All right. Let me make sure that the sound is working, and then we will start. I should unmute my, I'm gonna check the, it should be working. Okay, so let's begin. And I'm Alex Shim, and I'm representing Data Cabinet. And what I'm doing, well, let me first explain what Data Cabinet is. And I'm getting an echo from, because I have YouTube live on, so let me mute that for a second. Anyway, um, so Data Cabinet is it's basically it's an online service which allows us to well it allows us to do cloud computing online, and it prepares uh, it has pre-prepared environments with pre-installed dependencies, so you can, even if you're not at a computer, if you don't have uh, some sort of supercomputer or a lot of GPUs, or if you don't have a lot of computational power, you can still remotely run programs and it could be R programs for statistics, it could be Python programs, and in this case, it could be deep learning. You could be running deep learning models and algorithms, and in this specific case, reinforcement learning. Um, and the benefit of it is that you have access to you have access to CPUs online. You can actually you could literally uh, try to fiddle around with some algorithms on your phone using a browser, and then try to get it to work and just let it run. And you're not going to, and of course, since all the computations will be done remotely, then you're not limited by your own hardware. So it sort of gives this sort of democratic universal access to computational power. And so let me, so last week, let me go over let me just mention last week we went over I did sort of an introduction to reinforcement learning, and I focused on Q learning. And there are a lot of concepts there, and I'm hoping that this week that I'm going to try to keep it a bit more um, hands-on. I guess more learning through actually the notebook itself, and that may or may not be better. And you can think of it in a reinforcement terms as it's sort of an action that you could take. Do I want to tend towards these more um, like more applied actions, or should I do it, or should I be more worried about the theoretical concepts? And then maybe the outcome is how much the general audience, the average audience member gets back from it. So anyway, so last week we played around with some of the OpenAI environments, and we also talked about the basic the environments, agents, rewards, actions, states, the basics. And just so that people aren't, just so that people are a little bit more comfortable with what's going in, I'm just going to briefly mention most of these. And so first of all, if we remember from the basic Q learning example, where, I mean, you made an environment, and then um, you took in an action, you took in an observation, and then uh, you chose an action, and then you fed that back into the environment, and then the environment sort of updated itself and gave that information back to you, and it gave you a reward. But anyway, you could think of it in the simplest terms is that reinforcement learning is you have an agent, and which is choosing an action, and you have an environment which is giving back an observation for once it evolves to a new state, and then it gives back an observation, and you sort of observe the environment and get an observation for that, and you get a reward. The agent perceives the observation and the reward, and then you just repeat this process for each time step. And as I mentioned before, the basic terms, which hopefully people will get more and more comfortable with as they work on this and they read a little bit more about reinforcement learning, is that you have an agent, which is who or what's controlling your behavior or making your decisions. You have your environment, which is basically the entire system except the agent. We separate that. The agent is affecting the environment, and the environment is giving back information, which the agent then uses to decide on their next action. And the action is what the agent decides to do. The state is you could think of it as a description or a sufficient summary of what's going on in the environment. And there's a policy related to the action. There's a policy which is given a certain state, what action do I decide to take as the agent? And the reward is, well, the environment gives back a reward, and the agent uses that to shape their behavior, and with the goal that you're trying to maximize your reward or minimize cost. So those are the basic terms, and of course that's just more, it's not meant to be a full overview, but more sort of as a reference. And I wanted to, so I'm going to be working mainly in this, do I have a name here? I think I called it policy gradients, this policy gradients notebook. And I'll be giving sort of a high-level overview of what's going on and what we need to build in order to make a policy gradient reinforcement learning algorithm work. And I'll also just sort of give a short description of just some of the pieces that you that we're working with. Excuse me. Anyway, so let me start here. So we began our notebook, and I believe that there's some requirements that people have to do for their own versions, and I can, maybe Pankaj can give it in the chat, but basically it's about you have to do an extra command to change the directory to the gym directory where we installed all our OpenAI libraries, and then install all the environments from that directory using the command install -e. Well, I can mention it later, but well, actually, let me put it in chat. So the first line would be like cd gym, then install -e. Anyway, so anyway, we have our basic. Oh, and also the general assumption is that you're somewhat comfortable with Python, and for this workshop or seminar or workshop in particular, it'll be much more helpful if you sort of worked with, or at least played around with TensorFlow in the past. If not, I'm going to give a sort of like just a very general overview of what we're trying to do in TensorFlow, and hopefully that you'll be able to sort of live with the haziness involved there of not knowing, of not having used it. And of course, you can, as you can see here, TensorFlow is already installed on a lot of the data cabinet environments, in particular the projects that I've shared. And you can just import TensorFlow and just start playing around with it and just building computational graphs and doing calculations and so on. So we start with our basic import statements, and also we're going to import NumPy, which is what you generally use for computations in Python. And we're going to import TensorFlow, of course. And so let's play around with Tensor. To begin with, then, we have to know how to use TensorFlow, and we should be comfortable with it. And so I guess this is going to be like sort of a very short description or this is just going to be us playing around with TensorFlow in order to use. So let me go over what TensorFlow is on a very minimalistic basis. TensorFlow, you are basically you have variables and you're building functions out of the variables, and I'll give an example later. And basically, the first step is that you're building some sort of computational graph for a function. And then, for example, if I scroll down here, I will be building a policy using TensorFlow. I'll be building a policy which takes in the state variable and then outputs probabilities of actions, a vector of action probabilities. And you can see here that this is, I mean, you may or may not be comfortable or be familiar what the functions do, but you can sort of have a high level idea of what's going on. We define a weight matrix, we define a vector of biases, and then we're just multiplying, we're just doing matrix multiplication. We're just doing, well, it's W equal W times the state plus B. So it's just matrix multiplication. And then we're applying a nonlinearity function, which is what makes deep learning through through the function ReLU. You can also, there are other things you could do, a sigmoid function, and anyway, and then we're taking a softmax of that, and that's getting our probabilities. And what you should take from that is that it's very similar to Python. You're defining a variable using a function and some previous variables that you should already know, and then you calculate another variable on top of that, and then you calculate another variable on top of that, and finally you get the function that you want or what you're interested in, in which case it's just the probabilities. So that's building the computational graph. That's an example of building the computational graph. And in a simpler way, you could just take input and then you could just square the input, and that's also a valid computational graph. And if we go back to, so if we go back earlier in this, back to where we were before. So you build a computational graph, and then for TensorFlow, you don't actually have to define the variables, or you don't have to, it doesn't actually execute the calculations within the computational graph at like when you've defined it. So what you do instead is that you will start a session. In this case, for Python scripts, then you're just going, there's a different session which will just sort of automatically run everything through it. But they also have something called the interactive session. So you'll call tf.interactive session and define that as session, and then you can define some variables or some computational, or define your computational, or you could define a variable, and then you can just execute. You could call the run command on the session, and then if you put a variable in that as an argument for that run command, it will evaluate that argument, and the run command will make all prerequisite calculations to calculate that variable. You may have to feed in some basic input, but assuming you have like the necessary basic input, it will parse. You don't have to tell it to calculate all the intermediate variables. It will do it all for you, and it will calculate the variable that you're interested in. And that's oh, I misspelled this. And that's generally how. So that's sort of like the easy way of thinking about how you can use TensorFlow, and you don't have to use it for deep learning. You can use it for any sort of calculations if you want, and you can just play around with it and just do some just make some basic like mathematical functions, and it will handle that all for you. And the last step, which we'll talk about a bit more later, but which isn't important quite yet, is that there's a command called tf.train, and you can call an optimizer, which is, so this is the sort of algorithmic part. I mean, you've defined a variable, but you've defined some sort of function, but you want to adjust the function so it will optimize. For example, for image classification, if you get input, you want to map it to labels. So you want to change the function so it maps to the labels as closely as possible. Or more accurately, you have some sort of objective function. You're trying to maximize or minimize this objective function, and you're going to use iterative updates using the tf.train command to get as close as possible to your target, or to maximize or minimize your objective. And I know not everyone. That's if you're already comfortable with TensorFlow, then I mean, it should be fine. And if not, then you can. This is definitely a you could just play around with it in Data Cabinet. All you need to do is import TensorFlow, like at the top here, and maybe oftentimes they'll use NumPy or whatever. And you can import TensorFlow, and you can just sort of define variables and play around with it and just sort of get used to it. And there's, of course, a lot more specifics involved, but you can, I mean, you can work around with that yourself, and there are also some online tutorials for that. And so next, I wanted to actually, I really want to go to this sort of high-level overview of what we're trying to accomplish here. So what is a reinforcement learning algorithm? I mean, we've talked about what is reinforcement learning, but then if we want to actually create an algorithm which is going to try to the agent how to do something optimally, and maybe that will be, in this case, they'll be playing this sort of Atari game, or it would be playing this game of cart pull, but it could be chess, or it could be some Atari game, or it could be like some robotic simulation where you're trying to walk as long as possible, or learn to walk. And so the very high level way, which we actually mentioned last week, of what we're doing for a reinforcement learning algorithm is this process called policy iteration. And it's this sort of it's a cycle of policy evaluation and policy improvement. And like I mentioned before, the policy is what the agent uses to select the actions. And so for policy evaluation, what you're doing is that you're determining some sort of value function for your actions. And the value function is basically this sort of average, the average value, like once you reach a certain state, running then how valuable, like what would you expect in terms of future rewards once you reach that state? And if you think about it, I mean, this obviously depends on what your policy is, because your future actions are going to be dependent upon what your future rewards are going to be dependent on your actions. So let's say if you have if you're trying to walk and then your policy is just it just like crashes you straight into the ground and get like no rewards, then basically all your states are just terrible, because all your states are going to be, except for the brief state where you're standing up, all your states going to be just going to end up with you just with the robot just falling down and hitting the ground. So whereas if you have let's say if you have a policy which is actually good at walking, the most stable postures, I guess, of the robot or humanoid figure will actually have a good value function. And so last week we briefly talked about we briefly mentioned value functions, and we talked about Monte Carlo estimation, and there's also temporal difference learning. And although I didn't go over the last one, but that's not what we're as interested in. Next week we'll be probably more interested in that in something called actor-critic algorithms. But for now, we just have to know that, well, the one step of policy iteration is to evaluate our policies. It's determine how valuable all the states are. And the second phase, which is of more interest to us, is policy improvement. And given that you have you've evaluated your policies, now you can determine how to make them better. And that's sort of the essence of learning. And so for policy improvement, last week we were talking about Epsilon greedy policy improvement. This week we're going to focus on policy gradients. And I mean, that's going to be the main focus of the lecture, or this talk. And finally, I guess once you've improved your policy, now you can the last part of this you could think of it as this three-step process. You have sampling, you have policy evaluation, you have policy improvement. So once you've evaluated your policy, you've improved your policy, and now that you have a new policy, you're going to do some more simulations or rollouts. You're going to do some more sampling, and then you're going to use, and then you'll feed that sampling back into your policy evaluation in order to determine, well, evaluate the new policy. And then this process goes over and over and over again. Now for this specific case of policy gradients, I wanted to sort of break down what we're going to try to accomplish in creating a policy gradient algorithm. So the main thing is, let's see. Okay, so if we try to break this down into let's say sort of a more of a workshop level, if we're going to try to policy gradient algorithm, the first thing that we need to do is that we need to create a policy function. And a policy function, as I mentioned, is going to take the states or observations and output actions. In last week's case, we had a frozen lake example, and we were able to define, we had a 4x4 grid. I didn't evaluate this, but anyway, we had a 4x4 grid, and we could define the value function for any possible grid. But in the case of, once you have continuous state or observation spaces, I mean, there are infinitely many states, so you can't reasonably define them all separately. So what we're going to do instead is we're going to create a policy. We're going to, but then on the other hand, even if there are infinitely many states, there could be one state and there could be another state which is slightly to the right of the previous state, and then it's so close that it will make almost no, or at best a very marginal difference in terms of what happens with the policy. So we can imagine that we could probably create some sort of smooth continuous function, well, some continuous function which is going to, which we won't have to define for every possible state, but we can use some sort of parameterization, like it could be like XY coordinates, and then you could take in the XY coordinates and then you could output some sort of action. And I guess that's the basic idea of a policy. So let me sort of make sure this is all running. We can play around with TensorFlow on this line. In this line here, we're just going to do what we did in at the first lecture. We're just going to run just a very basic simulation. We're just going to run the cart pull environment, and it's taking random actions. So this is a random policy, and it's going to display a nice little rendering of that. So we want to create a parameterized policy function. And then once we have a policy function, what we can do is, well, now that we have a policy function, for any state, the policy function will give us probabilities for each possible action given a certain state. So once we know that given a state, we have the probabilities for each actions, we can sample from those probabilities and determine our actions or stochastically generate random actions, but random actions according to our policy function's probabilities, if that makes sense. But what that means is that instead of in the original example, instead of using this just sort of completely uniform random action, taking a uniform random action, we can take actions according to our policy and the policy that we've already defined, and later on we can adjust that policy and sort of change the probabilities. So we want to create a policy function. We want to be able to sample from that policy, and then we want to, once we can sample from that policy, we can now use that to replace our dumb sampling action with a smarter sampling, and we can do something called rolling out our trajectory. So we'll just take the we can just reset the environment, set it to some initial state, and then just have it just have it progress according to the policy. It'll arrive at a state, and then we'll let the policy function determine what action to take, and then it'll go to the next state, and then it'll use a policy, and then it'll use a policy to take the next action. They'll go to the next state, and so on. And the set of states and actions, and that's called the trajectory. And once we have those trajectories, we basically have our sampling, which we needed before for where was it? So once we have our trajectories, we have our sampling, and when we have sampling, we can evaluate our value functions. And let's see, where is it? And once we have those value functions and trajectories, we can empirically calculate our policy gradient. So we'll have an objective, and we're going to optimize our parameters using the data from our trajectories. And we'll be using the gradient of the policy with respect to the objective function in order to improve our policy. And that's the last step. Use a gradient to update your policy, which is the training function, which I mentioned before in the TensorFlow. So hopefully that makes sense. It's probably if you're watching this on video, then it's probably a good time to just stop and think about it a little bit, because I want people to, instead of just having just a lot of code and just looking through it and saying, okay, that makes sense and that makes sense, to be able to plan, to understand what they're trying to plan for in terms of building this algorithm, instead of just copying it. Like if they were to make their own algorithm, then the logical notion would be well, I need to create a policy function, and I need to be able to sample from it in order to roll out trajectories, and then I have to actually calculate the policy gradient, and then I have to update my policy. And this notebook is actually built around this sort of constructive way of breaking down policy gradients. Oh, let me go back to, so I'm going to, the example that I use for policies, for TensorFlow functions, I'm going to show it again here. And so our first step is that we're actually going to try to create a policy, pi of theta. So we're going to define the probability of choosing a certain action given we're in a certain state. And you don't have to use TensorFlow to do this. Honestly, all you're trying to do is you're trying to create a function which takes in state and then outputs probabilities. And you can easily use NumPy for this, but later on when we actually want to calculate the gradients, if you use NumPy, then you actually have to manually tell it how to calculate gradients with itself. Whereas with TensorFlow, if you define everything with a computational graph, then usually it can take care of it for you, so you won't have to worry about it. So this will make it a little bit more complicated for people who haven't used TensorFlow, but in the long run, it'll be a little bit easier, and hopefully I can provide some sort of slide explanations which will keep it accessible. So we're defining a policy vector, a policy function here. It's taking in some sort of state. In this case, we can see that at this last line of our example for cart pole, it outputted the observation. This observation is a 4-dimensional array. So what we're doing here is we're taking in our state vector, and then this line here, this expand dimensions, it's because it's to make sure that it's to make sure that it when we use TensorFlow, we're using some of the functions are a little bit pickier about the data type, so it's more to just make that work. Variable scoping, this you probably don't have to worry about this too much, but basically it's just a way of keeping your variable names very organized. TensorFlow has this sort of organized process for naming variables. For example, I call this, since I use variable scope policy, the actual name of the variable in this computational graph will be policy underscore W, and the variable name of this of B in the computational graph will be policy underscore B, and you can also nest these together, and it'll become, so it could be with variable scope A, and then with variable scope B, with variable scope C. It'll be on A underscore, or I think it'll be A underscore, or A underscore B underscore C, and so on. But that's some more technical things. But the more interesting thing is that I'm just trying to create a very simple linear function. So I'm just going to take our vector of actions, or our array of states, and then I'm going to multiply it by some sort of weight matrix to change it into the actions, to change it that maps to the dimensions of the action space, which is, so the observations are a 4-dimensional array. The actions are going to be either it's just you either go left or right. So you can think of it as a discrete 2-dimensional space. So what I'm doing here is I'm just matrix multiplying the state vector by some weights, and then I'm adding in some biases. So just a simple linear function. And as you can see, that's exactly what I'm doing here. I'm matrix multiplication plus biases, and I'm going to add in a nonlinearity, the most common one. Well, they used to use sigmoid a lot, although you'll see a lot more, especially for convolutional nets, they'll use the rectilinear unit, and that's basically just a linear function which is zero. It's for everything. It takes in some sort of input, and if the input is less than 0, then it keeps it at 0. And if it's greater than 0, it just the identity function. So it's this sort of flat function which below 0, and then above 0, it abruptly changes to just the identity function. And then after that, so that's creating a linear map so it's giving me some sort of scalar value, which is going to be, but then I want to, that in itself isn't really a probability. So we're going to use a common practice of deep learning for calculating discrete probabilities, and that's using the softmax function. And I'm not going to explain that too much here, but basically, it's going to, we're going to take so this linear map with this rectilinear function, it's going to give me 2 scalar values, and I'm going to use these scalar values as some sort of weighting for the probability of one action and the probability of the other action. So this probabilities variable is it's going to be a two-dimensional. It's going to be a 2-dimensional array where that represents a probability. So if you add both probabilities together, they'll add up to 1. And finally, this policy function is going to return the probabilities, this sort of probability vector. So that should be, hopefully that's not, if you're familiar with deep learning, then that shouldn't be too, or machine learning, or then that should be, you should be pretty comfortable with that. And if not, then you can just sort of read about it a little bit more and play around with it. But the most important thing is that, okay, you have a function, and then you return action probabilities. And then, so let's test if this worked. In this case, we're going to take our last observation, and then we're going to play around with our TensorFlow a little bit. So we're going to, so like I mentioned earlier on, we have to initialize our variables, and then we have to run the initializations, and then we can just run whatever function that we want. In this case, we're going to run the policy function on our observation. Okay, and so in this case, so we're gonna test out our new policy function, and we're gonna output probabilities for going left and probabilities for going right. What happened? And I got some sort of error. Oh, I didn't run this. Okay, I got a strange failure. This didn't happen before. If I can fix this quickly, and if not, I'm just going to keep moving. Let's see. Uninitialized value. Oh, okay. Anyway, that's a small error because basically, usually in TensorFlow, you initialize all your global variables at once, and they used to have an initialize all variables function, but it was deprecated. So we try not to use that. So the way I tried to fix it was by since a lot of these variables, for this policy function, a lot of these variables are actually local variables for the policy function. I tried to add in this local variables initializers line, and so it doesn't work the first time, but then the second time I run it, it kind of like it properly has initialized both the local and global variables, and it ends up working. But anyway, so we can see here that I ran this, and then if I want to actually evaluate, so if I just run policy observation, nothing will happen because that's just a tensor. So I need to run session.run and then the variable, and then I can actually get the value of the function. So in this case, it's going to be the probabilities of 0.244 and then 0.756, and you'll notice that those add up to 1. So that means it's going to, if we sample from this, about 25% of the time it'll pick 0, or it'll pick left, and then 75% of the time it'll pick right. And I just wanted to point out this is different from so if we had a 50-50, if we had a fair coin, so it's probabilities 50% heads and 50% tails, you don't sample from it by saying, well, my probability is like I sampled from it, and for my one trial I got 50% heads. That's not how it works, because when you actually do a trial, it's going to choose one action or the other action, but it's going to choose it depending on the probabilities. So that's just saying that defining the policy and the probabilities is not enough. You actually have to sample from it appropriately. And so that brings us to the next step. So if we have a policy that determines probabilities for each action, but we actually need to do the sampling. And normally we would use something like NumPy has a bunch of random functions. And probably the one that's most interesting to us for choosing discrete actions is random choice, because you can feed in action probabilities. You can feed in a set of probabilities, and then based off those probabilities, it'll output one of the actions. But since we only have 2, there's a much simpler way to do this. All we're going to do is we're going to pick a random number between 0 and 1, uniform random number. And if our value is lower than the first probability, then we're going to set it to 0. We're going to define our selected action as 0. And if our number is greater than our first value, which is 0.244, we're going to set it to 1. So that's just a very simple way of doing it. In cases where there's more actions and you do something, well, you probably use like random choice, or TensorFlow actually has some random sampling functions as well. So we're going to define this policy for sampling. Sorry, I already did that. Let me scroll down. So this is policy action. We're defining a new function which is going to select actions or sample actions. So we take in our observations. We need to make sure the data type fits properly. So we have this sort of hack to change the shape of it. So the TensorFlow will accept it and do proper matrix multiplication with it. And we're going to do our selection based off of what I mentioned before. And so let's test it. Okay, I didn't define it. Oh yeah, I defined policy action, and then our observation was, we took our observation, and then we know that around 25% of the time it's going to be 0, and about 75% of the time it's going to be 1. We could actually just run this a whole bunch of times if we want. You could loop it if you want to do it faster, but we're choosing it here, and we can see that's changing 1, 1, 0, 1, blah, blah, blah. And if we did this like infinitely many times, then it's going to average out to the action probabilities. I mean, that's how probability is supposed to work, at least. So what have we accomplished? We've created a policy function, and we've created a function to sample from the policy function. And so now this is great. If we think about the basic OpenAI example, what we were doing is there were 4 basic steps. We had to make the environment, okay, and then we had to reset the environment to some sort of initial state. We had usually we render the environment, and this is our way of, cart polls is a bit difficult, so we had to install certain libraries and workarounds in order to make it work. But this is basically environment render. And then we choose an action, and then we take a step. The environment takes a step based off that action, and it outputs the observations and the rewards. So that's basically the simplest way of using OpenAI Gym. And all we're doing here is now that we can select actions, we're going to use policy action instead of a random action, instead of this random sampling to choose that action. And so you can see down here, we're going to define this rollout function, and you can see there's a lot of stuff here, but the most important parts is that, okay, so it's exactly the same as before. We reset the environment, and this is just some hacks for the display. These lines, total reward, states, actions, transition, future rewards, this is more so when we, sorry, excuse me, I have to sneeze a little bit. Okay, so moving on, so continuing, what I want to do is I want to do this rollout. So I want to use my actions to just sort of allow the simulation to run, and those relevant lines are going to be reset, and then we're going to choose our actions here. So over here, we're going to set our action, define the action that we're going to take is by policy act observation. And then we're going to take action, environment, step, and action. And for future use, we're going to we initialize a total reward as 0, because we do want to know. The idea of policy evaluation is that we want to, if we run our policy for a while, we want to determine how well we did. So we're going to define some sort of total reward, and we're going to when we run environment.step, then we're going to get our observation and our observation and reward for each time step. So we're going to update we can record our total reward by adding our reward, this single time step reward to and accumulate as a sum. The other part is that it's going to be useful for us to record this information. So we're going to record a list of the states, the actions, and the transitions, which is going to be the state action reward triplet. And for future reasons, we're going to be interested in, we're going to record the future, instead of just a total reward, we're going to create the future rewards for each time step. So for the first time step, our future returns is going to be the same as the total rewards. For the next time step, the future rewards is going to be the total rewards except for the first reward. So it's going to be R1, it's going to be like R2 plus R3 plus R4. But then for time step 3, it's only going to be like R3 plus R4 plus R5 and so on. So we're combining these two pieces of first of all running this rollout and also of recording this data. This code here is just it's the exact same hack as before for rendering it properly, and down here, we created a, so the observations of four-dimensional vector, these actions that we're choosing, they're just 0 or 1, but actually it's often more helpful for us in this discrete case to call something called the one-hot version of discrete actions. So instead of saying that out of action 0 through 10, we chose action number 5, what we're going to do instead is we're going to create a 10-dimensional array. And so if we chose action 5, we're going to set the index of the fifth index to be 1 and all the other indices to be 0. And so instead of creating, because, and the rationale behind this is that instead of having a number 1 through 10, we have now this sort of 10-dimensional space, where if you take action 1, then it's sort of 1 along one axis, and if you take action 2, the value is 1 along the second axis and 0 along all the other axes. And it's sort of, I mean, well, there are reasons behind it, but generally that's how it works because it's more flexible. So we're going to record the actions, but I just wanted to point out we're not going to record the numerical values of the actions. We're going to create the sort of vectorized version of the value of the actions. And yeah, so yeah, and there's also a done flag. For environment step passes back a done flag, and a done flag means that you've reached a terminal state and there's no reason to keep on continuing rolling it out more. So so you can see here that we have this loop. We created a loop of I believe 200. Yeah, for an X range of 200, and then but if our scenario stops early, action will pass back the break command, and we won't have to keep iterating pointlessly. It'll just stop it for us. So, and finally, for our particular example, because we put in this effort to be able to see this. So I created this. We're passing in the environment as one of the arguments to our rollout function. We're passing in the session. So because it has to, you can't. If you just define the function, it won't evaluate itself. You have to tell TensorFlow to use session to evaluate the value of one of your TensorFlow variables. And we have this third argument for rendering in case I want to actually visualize what's going on. If you're actually just running the reinforcement learning algorithm, you don't actually need to see what's going on. So you usually won't see this. But I think for a notebook where you're playing around with it and you want to see if it's working or not, then I thought it would be helpful to add in this sort of third argument, which would allow you to turn on and off this visualization. And so let's make sure. So I executed this. Now I'm going to use this rollout function. And as you can see here, okay, I think it ended a little bit early. Oh no, sorry. So it ran the simulation, and I think this one has it ended already? Yeah, it ended already. So so if I roll this out, you can see that it's moving a little bit. It's using the policy, and then it's passing back the information that I'm interested in. And because I wanted to sort of for debugging purposes and also to understand what's going on a bit more clearly, sorry. Okay. There is a question, and I want to make sure. Okay, increase resolution. Well, actually, sure. Okay. I'll just do it. right now, and hopefully that's, I'm just going to zoom in a little bit because that's a little bit quicker. I'm checking the YouTube video, and okay, that's way too much. Okay. Hopefully that's reasonable. Okay, great. So I'm going to do, so I tested out a rollout function, and I also had it. So I mentioned that I was recording a list of states, actions, transitions, and total reward, and I just wanted to see what to. I had it return it just so that we could see what's going on, and we can see that. Harder to scroll, but that's fine. So this first set of information, it's going to be well, anyway, so, oh, sorry. Sorry, my throat gets a little bit dry. But anyway, so we can hear this this array of 4 dimensions. It's going to be our states, and if you go down a little bit further, we'll see the next array is just zeros and ones, and actually that represent our actions. So if it's 0, 1, it's going to be left, and if it's 1, 0, it's going to no. So if it's 1, 0, it's going to be left, and if it's 0, 1, it's going to be right. And then this next one is this triplets that I was talking about, and it's just going to be the states, which is this 4-dimensional vector. And then it's going to be 0 or 1, and I believe there should be rewards as well. And then, sorry. And I think at the very end, it should show total rewards, although it's not super important. But anyway, zoom out a little bit just to scroll down properly. Okay. Sorry. I'm going to zoom in a little bit more. So anyway, so now we've done our rollouts. We've tested it. It's actually working. So it's taking the trajectories that we want, and we're recording our states and actions and trajectories. So remember, the next step was to our next step was that in terms of what we're trying to, in terms of our workflow. I should zoom in here, but anyway, is that we want to. No, this is not right. Sorry, we want to, so we created a parametrized policy function. We've sampled from the policy, we've created a rollout and recorded the trajectories. And then the next part is that we actually have to calculate the policy gradient. So that's the next function that we're going to try to prepare. And this is probably the most theoretical part of this workshop. And usually you'd spend a while like doing algebra on a blackboard and showing it. But hopefully I'm going to show a short simplified version, and not all the details are going to be like, it won't be obvious how you get from one step to the other, but if you just sort of but hopefully you'll be somewhat comfortable about it, and you can actually learn more about it yourself. So we're going to talk about the policy gradient calculation. So what our objective is that we're trying to maximize our future rewards. So we're going to maximize our rewards over all the time steps. So that's, in some cases, going to be maximize our discounted future returns. And of course, we are going to be this, and we're maximizing it, but over our distribution of our policy distribution. So we're not going to, it doesn't necessarily make sense to do it for one trajectory, but if we average it out, then it's going to give us the average expected future returns. So for one single time, so the simple way to think about it, or the way you break this, the way you break this down is that for one single time, you consider it for a specific time step, and where you're calculating just the reward, one specific reward, and that's just the expectation of the reward given state S in taking action A, which is E of R SA. So this is sort of our single time step objective, and what we're trying. So if this is our objective, if we apply the gradient to it with respect to to the parameters that we're interested in, so in this case theta, because our policy pi is parameterized by theta. Did I do this right? Oh, this shouldn't be pi theta. This should just be theta. But anyway, so this should just no, this is right. Sorry. Okay, yeah, this is a different thing. So we want to take the expectation, the gradient of our single time step j of theta. And the question is, how do we do this? Because, well, theta affects, the problem is that our expectation is based off of, oh, that didn't highlight well at all. It depends on our actions in our action distribution. Our action distribution depends on pi of theta. So in one sense, like you should feel a little uncomfortable taking this gradient and just moving across this expectation, because you have to consider, well, as I change the expectation, as I change the policy. So if I'm changing the parameters theta for the policy, then I'm going to be changing the expectations distribution. So how do we deal with this? And there's a trick called the score function trick, and it's that you can move this gradient across the expectation, given that the expectation is based off of the distribution pi theta, by taking the gradient by you use, sorry, the gradient of pi of theta it'll become, sorry, the gradient of the expectation of pi of theta is going to be, it becomes the expectation of the gradient of the grad log probability of pi of theta. And the reason why this works is that the derivative of of a log function this is just going to be the gradient of pi of theta divided by pi of theta. And so actually, if you think about how the expectation works, then it sort of cancels out. Okay. Yeah, it will be. It is all available on YouTube, Cyril, and yeah. So hopefully, yeah, you can access it at your own leisure. I think this is the hardest part, and it's a little fuzzy. This policy gradient, it's a little bit fuzzy. So I'm just sort of giving this overview of how it works. It probably won't make perfect sense initially at this time. Sorry. Um, but but anyway, this is called the score function trick, and so okay, this is a score function trick. So our expectation is going to be it's like pi of theta times the reward of SA. So if we use the score function trick, we can swing this gradient operator into the expectation by changing this pi of theta times R to grad log pi of theta times R. So now our objective we can define. So now when we minimize our objective, we know what this expectation, we know how to calculate this gradient, and we can, the way we calculate this gradient is just instead of using, we're going to use this grad log probability, and we're going to multiply it times the reward function, and we can do this step by step, and this will give us our parameter updates. And I don't know if you guys are comfortable with that, but that's the derivation. And I'm going to make it a little bit more uncomfortable and hand waving because I'm not going to explain the next part, or I'm not going to derive the next part. But basically, if you consider all the time steps together, I mean, that was for one time steps, but if you want to consider all the time steps, there's something called the policy gradient theorem, and you replace this reward with future rewards, or equivalently, it turns out that you can replace, I mean, if you remember what a value function is going to be the future rewards from a given state. So you can replace it with future rewards or the state value function, or you can also replace it with the advantage function. And there is this interesting paper by Andrew Ng, who did, I think he did the machine learning course. So he wrote a paper in 2000 explaining why you could use an advantage function instead of a value function. And an advantage function is, you don't have to know this, but it's the value function, it's the value function of a certain action minus the minus sort of like the base value function. And the idea, actually what Andrew Ng proved was that if you have a baseline which function which satisfies certain properties, you can reshape your rewards with a certain sort of with a certain baseline function, and it'll preserve the structure of the MDP. I mean, it's interesting theoretically. It's not that important to know now, and we're actually not going to get into this until the actor critic. Technically, a lot of the algorithms which use policy gradients will use the advantage function instead of the future rewards or the value functions. But I think for this workshop, I think future rewards is the most it's the most accessible variant of it. It's the most, you can sort of get an intuitive sense of what future rewards are, whereas if you don't know what a value function is or an advantage function, then you'll be less comfortable with that. But anyway, so we know how to calculate. So this actually allows us to calculate the policy gradient. We can take, if we know, if we can take the grad log probability of our policy probabilities, we can multiply it by rewards or what we're using instead of rewards, which is going to be our future rewards, which is so if we're at state t, then our future reward, we can replace our future rewards with RT plus gamma times RT plus 1 plus RT plus 2 and so on. And this gamma is just this discount factor. And if we use this variant where we're using these sampled future returns, we get what's called the reinforce algorithm, which is a very famous reinforcement learning algorithm, I think from the 1990s or something, maybe earlier. And it's using the exact same formula that we had before. Well, pretty much the same formula. We're taking the grad log probability, and then we're multiplying it times our future returns, G of t, and then we're going to use that as our gradient step, and then we're going to update theta accordingly. And so ideally, you would know what how gradient descent works, but basically the idea is for a gradient descent is that a gradient is the direction of steepest descent or ascent. So it is, the gradient of a function will point in the direction where it increases or decreases most rapidly. So if you want to reach a local like minimum or maximum, then if you move in or against or directly against the direction of the gradient, it will point you. It will move you to that local minimum or maximum the quickest, at least locally. In practice, then the space could be a little bit funny, so it might be a bit more circuitous. But the basic principle is that if you take the gradient, if you keep following the gradient, you will eventually reach like the top of the hill or the bottom of the hill, and that's exactly what we're doing here. That's how stochastic gradient descent works, and that's pretty much how the vast majority of deep learning algorithms work. They use gradient descent in order to update the parameters of their functions to optimize it. So that so anyway, so the reinforced algorithm, if you went through all that, and if you're even somewhat comfortable with it, then you'll get the idea is that, okay, the most important thing is that we can update our policy parameters theta using this equation, and we can, all we have to do is calculate the log probability of pi of theta, which actually TensorFlow will do for us. You just have to call the function like a tfnn log pi of theta, and you multiply that by your future returns gt. So in order to calculate the policy gradient, all we have to do is calculate future returns and then multiply that by our grad log probability of pi of theta. And so that's what we're going to try to do next. And that was our long theoretical explanation. Anyway, so yeah, we're going to be trying to use this Monte Carlo version of policy gradients, which is called reinforce. So we're going to calculate the future returns. And to do this, so remember before when we did our rollouts, we recorded our states, actions, and our transitions, and we're actually going to use this stored information to calculate the future returns. So remember that our rollout function passed states, actions, transitions, and total rewards. So we're going to get back those values in this first line here, and then we're going to I didn't have to do this, but total reward to 0, which is probably a little silly. We're going to define this future returns vector array, which is yeah, we're going to define this future returns vector, and the way we're going to calculate this is that we're going to enumerate through our set of transitions. Remember, our transitions are triplets, and we're going to go through them in order. Each transition will unpack into observations, actions, and reward, and then for each particular time step, we're going to calculate the future returns, and we're going to do that using another for loop. So we set let's say our future reward to 0, and then we have to determine, well, how many iterations, how long do we have to, in our inner loop, when we're going to go from, let's say, g of t to g of to g of big T, let's say the final step. We only want to do it for a certain number, so we're going to use the length of transitions and subtract by the index. So to determine, so we won't have to go too far, and we're going to decrease it. And anyway, so and instead of adding, if for the discounted version, it's going to be like gamma times reward plus gamma squared times a reward plus gamma cubed times a reward. But instead of trying to add that all up at once, we can sort of nest this together by just sort of adding the transition and then multiplying it by the discount factor, and then decreasing the discount and so on. But the most important thing is that this expression is going to evaluate to just be our future returns. And so we get our future returns, and that we for each time step, we determine our future returns from that time step, and then we're going to append that onto our list of future returns. So now we have our list of states, we have our list of actions, we have a list of transitions, and we also have a list of future returns. And over here, I ran this example, and yeah, if you can see here, and also this notebook should be available for importing. The idea is that you guys could have worked along with it either now or in YouTube, or sorry, or while you're watching on YouTube. And so what we see here is that we have this list of future actions or future rewards. It's going nicely for me. But anyway, let me expand. Okay, so if I expanded a little bit, so we could see that the future returns for the initial time step, it was 15, and then for the next time step, it was like 14.6, and then 14.06, and so on. So it's slowly getting smaller because the future returns it's only counting the future returns after that time step. So it's shrinking and shrinking, and we have a discount factor as well. But anyway, so in terms of our work, okay, I'm trying to expand this a little again. Okay, so in terms of our workflow, so we wanted to we created our policy, we sampled, we did rollouts, we stored trajectories, and in order to calculate the policy gradient, we needed to calculate our future returns and then multiply it by our grad log probability. So now we actually have everything that we need. So we just have to multiply our score functions by our grad log probability, and then we can calculate our policy gradient. So we're going to define a policy gradient function, which is going to sort of set up the computational graph and do all this work for us. And the earlier parts, it's just going to be the same as a policy function before. We have our weights, we have our biases, we have a placeholder. In this case, we want it, in order to calculate future returns, we have to feed in the list of states, actions, and future returns. So we have placeholders. TF placeholder is a TensorFlow function, which it doesn't have an immediate value, but you'll feed in um, information for this variable for this tensor, and it sort of takes a place of input, and then it'll proceed with the calculations as normal. So we have our same as our policy linear function. We have our nonlinearity, softmax probabilities, and then here is pretty much the gradient. A long explanation about policy gradients. That's pretty much what we're doing in these two lines here. So this first line, TF reduce sum. So let me explain this. So the score function is a log probabilities, but when we took our expectation, I don't know if I have a picture of it, but okay, well, it doesn't matter. So it was we just said grad log probability, or expectation of grad log probability times the future returns. However, the way it works is that we're only interested in the probabilities for the actions that we actually took, and we're going to ignore the probabilities for those other actions that we didn't take, because, well, that's part of the expectation of the sampling. So what we're doing here is that we're going to multiply our log probabilities. So our probabilities vector is it's an array the size of the action space, and we're going to multiply by the actual actions. And remember, the actions are 1 if it took a certain action and 0 for all other actions. So this will give us TF log probability times actions is just going to give us only the value of the log probability, of the action that we actually took, if that makes sense. So that's a short note. And the second part here is that, okay, now that we have this proper score function, and for those interested, TF reduce sum it's pretty much the same as NumPy sum. You're just, I mean, when we do this sort of multiplication of the probabilities and the actions, it's an n-dimensional array, but where only one of the values matters, which is the action that we actually took. But we're going to add those together. So we're only getting a single scalar value for the score function. So we take so policy gradient is score function times future returns. So we have score function times future returns. That's now our loss function. And now we're going to run, like what we mentioned before, our TensorFlow optimizer. So that's tf.train. We're going to use something called the Atom optimizer, which is probably one of the most commonly used ones in deep learning. It's basically a variant of deep learning which accelerates learning a little bit faster because it's more aggressive about it uses this concept called momentum, where it will, if your step size, sometimes you have, if you're doing you're updating theta, but then you keep going down. Let's say you have a big negative decrease for your gradient is a large step, and then you have another large step, and then you have another large step. Well, you could think, well, if I keep going, if I'm like, from the physics example, if I'm taking these large steps down a hill because then I probably want to go faster. So the idea of atom optimizer momentum is that if you've taken a lot of large steps for the past few cases, then you're going to take even larger steps. And if you're taking small steps, you're taking it'll shrink the step size. So larger. So if you're decreasing rapidly over time, then it'll increase your step size. And if you're decreasing slowly, then it'll shorten your step size. And anyway, so that's tf.train. You can choose, there are several optimizers you can use for TensorFlow. There's probably like a normal stochastic gradient optimizer. There's probably momentum, Nesterov momentum, just the common ones. And then, so we have our optimizer, we have our learning rate for the atom optimizer, and we're going to minimize, we have to tell it what we're minimizing. We're going to be minimizing our loss function loss. And our policy gradient function, we're going to, for the use of other functions, we're going to return the probabilities, which of course we need to do action selection, and then the states, actions, future returns, and most importantly, it's going to return this this optimizer function, which is, remember, we called tf.train. This is actually a function, so we want to get our optimizer function, this optimizer function, so that when we run, in our main algorithm, or when we actually execute this all to do learning, we want to run this optimizer to do our policy iteration, to do our policy improvement step to get our best possible theta value. So let me execute this. So TensorFlow allows us to use our optimizer to optimize our policy parameters. And then, and this last step, well, I believe this last step is, I think here I'm testing the policy gradient to see if it's actually doing the iteration. I think to make sure it's working properly. So we have our policy gradient function, but we're going to define that. We're going to define a new function called, or a variable called policy gradient, or a TensorFlow variable called policy grad through the policy gradient function, and we're going to pass back, and we're going to use our policy gradient function to create certain variables, which is going to be our probabilities here, our states, our actions, our future returns, and our optimizer. And like before, if we want to test this out, we have to initialize. So before we initialized our policy function, but now we've created this new policy gradient function, or a new policy function, which includes the ability to calculate policy gradients, this is the reason why it's different than the other one. This one actually has this optimizer, which allows us to calculate the gradients. So we're going to initialize this function, and then we're going to we have to run the initializations, and then we have to pass in the future returns vector, and we got this from earlier in the notebook. We calculated an array of future returns. We have to shape this properly, so we're going to use this NumPy function to do that. And then, so remember, what we're interested in is this optimizer, right? We're interested in our ability to train it. So we're going to run PL Optimizer, and remember, PL Optimizer, this last argument is just the optimizer in our policy gradient function. So remember what I said before, for TensorFlow, you define your computational graph, and then at the very end, you actually have to initialize the variables, and then you actually have to run it. So now we're running the function that we're interested in, this optimizer. And the funny thing about these TensorFlow functions is that, well, it looks like it doesn't have any arguments, and that's because that remember I said that for TensorFlow it sort of calculates everything from prerequisites, but you don't have to pass in the arguments for the prerequisites directly as arguments of, like, this isn't taking any arguments, but implicitly all that information is stored in the computational graph. Specifically, when we have TensorFlow placeholder functions, it's sort of waiting for you to fill in the inputs using this thing called feed dictionary. So I had for policy gradients, for the policy gradient function, I had let me scroll up. here. So I had placeholders for state, action, and future returns. So I need to use feed dictionary to fill in the variables for state, actions, and future returns. And I defined, and using this return function, I defined these variables as PL state, PL actions, and PL future returns. So I need to pass in those values. And I did that here. So PL state, I'll feed in our states array from our trajectories. PL future returns, I'll feed in future returns, our future returns vector, which we just created. And actions, I'm going to feed in the actions array, which from our trajectories. So now we've actually created, and we've created a runnable optimizer function for training. And so this sort of completes all the pieces that we have together. So we're going to combine them all into, so before we had a rollout, which sort of just, given a certain policy, it sampled actions and it sort of ran simulations given that policy. But now we're going to run a sort of extended version of the rollout function, which will actually include this policy gradient update, which will include policy gradient. So this is actually going to change the policy. It's going to combine the policy evaluation with the policy improvement, and then it's going to improve the policy, and then it's going to run it again, just like this. I believe that, yes. So this step here. So it all goes back to what I was mentioning before. There's reasons why I structured it this way. So we have policy evaluate. So our extended rollout, it's going to do our sampling. It's going to do our policy evaluation. And it's going to do policy improvement. So it's going to combine that all into one function. So rollout complete. I'm pretty much using all of these pieces were in the previous functions, or just the code that I had in this notebook. So we have we're passing a policy grad argument here, variable, and just like before, we're getting calculated state actions, future returns. We initialize the environment. We have some rendering option, which we probably don't need anymore, but it still might be useful to have. We're setting our total reward because we want to roll out to usually we'll want our rollout to return how well we did for that trial, just so we know, because it's just useful information. And then we have our states, actions, and transitions and future returns lists. Which we'll be using later, we're using to record our trajectories and later on pass that information to our policy gradient function in order to calculate the score times the future returns. Here is just, we're going to create a loop for simulate. This is the simulation step, or the sampling step. And okay, so this is just display, it doesn't really matter. We're selecting actions based off policy act, and then here we're just recording, we're selecting actions, and we're taking environment step, same as before, and we're recording those actions, same as the first rollout function. So nothing special here. We're calculating the future returns like we did before. Oh, sorry, scroll down too far. And then finally, then we reshape the future returns, and then we ran the optimizer, and that's it. So and then we ran the optimizer to improve our to update our policy parameters, and we're returning total reward. So that will do that single step of policy iteration of sampling, evaluation, and then policy improvement. And so now we have our great, wonderful function, and all that's left to do is to just actually run it's just run the rollout function for a whole bunch of steps. And so now we have our, so let's say we didn't have the sort of test code that we did to make sure it was working. So we're just going to create this sort of like fresh example. So to start pretty much from scratch, except for the predefined functions. So we have we define our environment, which is cart pull, and then we define our policy gradient through our policy gradient function. We start TensorFlow in interactive session. We initialize all the variables. Um, this is probably redundant, but it doesn't matter. And then we're going to run for, I believe, we're going to run for 2,000 steps. We're going to run the rollout. We're going to run the rollout for, I believe, 2,000 steps, or is it going to be 2,000 improvement steps? Might be 2,000 improvement steps, but anyway, we use our brand new rollout. Oh yeah, this is our policy iteration. So for 2,000 times, we're going to try to update our. We're going to sample and then calculate. We're going to sample and then we're going to do policy evaluation. Then we're going to use policy gradients to update our policy parameters. So basically, this is a reinforcement loop. For 2,000 time steps, we're gonna improve theta. And at the very end, we are going to just run the episode a whole bunch of times and like 1,000 times and see how well it works on average. And this is actually not very fast, but okay. It's working before. I didn't execute this. I didn't execute that. Okay. Okay. Future returns. So anyway, so now I executed it, and I didn't skip any steps, so I executed the code, and it is now running the simulations and then calculating the policy gradients and updating it. And actually, this is I tried to see how long this would take, and it's not going to finish in time. But I actually could interrupt this and then run out a rollout, but with a visualization, and it'll actually hopefully it would show a better it would show a policy which is like fairly adept, which is better than the initial. So it was initialized to some like not very good policy, but then after a while, if I run it for a while and then I test out the rollout function again, it will actually show like it should be pretty good at it. And you could actually like just do that in this line here after an interruption. So this is the full thing. This is a policy gradient algorithm. It has done all the steps, and it's right now it is as you can see through the line up here. It's running through. It's doing all the work, and it's slowly learning. It's learning. Our algorithm is learning to balance this pull on a cart. So. And I think that's, I mean, it's pretty amazing. Even though you could have this, you could put this all together. Of course, you might have to change the functions for different environments, but you could. I mean, this takes a while, so maybe you don't want to run this on your computer, but like you could actually run this on a cloud, like through like Data Cabinet, and while you're busy doing something else, like you are slowly you've created this reinforcement learning algorithm, which is learning to perform tasks for you. So it's pretty amazing. Yeah. So I guess let me ask if there is any questions or if there's anything that that people wanted me to go over more. And hopefully people find this. It should be. It won't be easy, especially if you're not as used to TensorFlow. But hopefully you can see how the pieces fit together and what we're trying to accomplish in each step. And yeah, and you could see where we're going with this, and you can, and it's also should be accessible enough where you can play around with each piece. and test each piece to see if it's working and to understand how it's working. And if you are viewing through YouTube, or if you think of questions after the fact, then you can just email us or contact us. Yeah, so I guess in terms of some final thoughts, it's that the policy gradient algorithms are, so last week we did Q learning with basically we sort of did this introduction, and then we learned how to use OpenAI to run simulations, and then we created these value functions. We worked on creating these value functions, or action value functions, and then actually I prepared a new notebook which it's called Frozen Lake Q Learning, which actually was a bit more comprehensive than what I had at the time. But basically, it can run Monte Carlo simulations to determine the value function for every single state action, and then at the very end, you can do something called what's called the Epsilon greedy update, which is you take for each state, you take the best possible action, and then you use that to define a new policy. So that's, instead of policy gradients, that's your policy improvement step. And I guess I want to connect what we're doing here a little bit, or compare and contrast. One is that for this policy gradients, we recorded all our trajectories, and that's actually something which is called or experience replay. You're using this recorded information as well. You're using it as samples, and you're using that sampling information, and you can use that sampling information to update your value functions or your policy functions. And so you can apply that similarly, and then the actual Q learning algorithm uses experience replay to instead of just like, so the version that I have here for Frozen Lake, it just does Monte Carlo evaluations for every single state. But for the experience replay version, you don't actually get to sample every single state, so you actually have to use your sampled information in order to do the Monte Carlo rollouts. And the comparison is that for our policy gradients, we have implemented something like this experience replay, so we could actually use that and then apply that to the Frozen Lake Q functions to make a more proper Q function learning. And the comparison would be for Q learning, what we did was we use this Epsilon greedy way of policy iteration. For policy gradients, what we did instead is that we have a parametrized policy function, and then we use our gradients and our future rewards to update our theta to maximize the future rewards. So both are methods of policy improvement. And although this is more, yeah, so I mean, but this policy gradients uses gradients, whereas Epsilon greedy Q learning uses this very greedy, more heuristical method of doing it, of improving the policy. The other comparison is that Q learning, it relies more heavily on the policy evaluation part, which is sort of estimating the value function or the Q function. Whereas this the version of policy gradients that we use, we weren't that concerned about the value function. We just use Monte Carlo estimates in place of value functions. For next week, there is sort of a branch which combines both the policy evaluation and the policy gradients together. So the problem with policy so the problem with these Monte Carlo estimations, let's say you have a game like checkers or chess, and your reward is, if you win, your reward is 1, and if you lose, your reward is 0. If you actually think about this code and the policy gradients and how we're doing this Monte Carlo steps, that's a pretty terrible reward, because you actually get you get 0 reward until you win. So even if you make a really terrible move, it's a Monte Carlo evaluation. Like if you get lucky and you win, you assume that, well, I guess all the actions that I took were good actions, and if I did, which is sort of the intuition behind what we're trying to do here. And if you lost the game, then you assume that pretty much all the actions that you took were sort of bad actions, and you lower the probabilities of taking all of those. But that's kind of dumb because it's very noisy. There's a lot of in statistics you'd say there's a lot of variance involved in terms of the policy gradient, because it's based off of whether you win or if your reward is just very weak signal at the end of just winning and losing, then you don't get a lot of information from that. So it's often better. It's usually, if you want to be less noisy, then what you use instead is a value function approximation instead of the future returns. So instead of saying that, okay, I made a move and eventually I won, you'll say I made a move, but from my understanding of the game of Go, I made a move and I put myself in this position where I think I have a probability of blah of winning. So that would be my value function. So I think it's better. I think the state that I arrived at by taking the action is worth more. So I'm going to use that information. So that would be the value function. I'm going to use that information to update my instead of just the future returns, and that's going to give me a less noisy estimate of it's going to give me a less noisy estimate of my future returns, and so hopefully learning will be faster because I don't have to if I'm only basing my decisions of learning based off of if I win or lose a game, then I have to have a very large sample size in order to sort of average out all that noise. But if I have this sort of value function approximation, then if I have a value function, then I can use that instead, and it's going to be a lot cleaner, assuming my value function is accurate. So next week we're going to do actor-critic algorithms, and actor-critic combines it. You'll notice that in fact, if you leave this running for a while, you'll notice that it's still running and it's not moving very quickly, or it hasn't finished quite yet, and it's taking a while. And so if we wanted to converge faster, then we probably want to use something which combines those two together, which is this actor-critic method that I was talking about. And in fact, we can use advantage functions, and we can use actor and critic, and there's actor critics. There's something called A23C and A23C, which is this asynchronous actor critic algorithm, and it's one of the along with Q-learning, Q-learning, policy gradients, and actor critic algorithms like A23C, they're some of the most popular reinforcement learning algorithms out right now, and you'll see that used a lot, and they're more advanced ones which solve different problems, which hopefully eventually we'll get to sort of try them out. But hopefully over these 3 weeks, if you can sort of somewhat get comfortable with at least trying to make each of these work, then you'll actually you've actually have a fairly being able to program the three most sort of like most standard types of reinforcement learning algorithms. That's a pretty big step. It means you're a lot closer to actually. I mean, you can realistically make a lot of reinforcement learning algorithms work. I mean, they may not converge very. There some. The more advanced stuff is more about like how you can make it converge better, or to make it more sample efficient. But yeah, I thought it was pretty interesting that we could sort of put together notebooks where we could actually make these sort of popular but fairly advanced and somewhat intimidating methods work. I guess that's all I have for now, and if there are any questions, let me know. If there's any technical difficulties, then we can help you with that. I am interested in any feedback on I guess these sort of presentations and notebooks. to see if I can. Everyone has different learning styles, and actually I have a more theoretical learning style, but hopefully this actually works better for people who just sort of want to like dig into code and just like play around with it and make it work. Um, but at the same time, it sort of gives some of the background for why it works and how to and also like how you would be constructing it together, and how would not necessarily even as a finished product, which would be this sort of very end line, but the end line of the policy gradients, but actually like how would you build it in pieces and then sort of test it out and make sure everything's functional, and then put it together and then create your reinforcement learning algorithm. um, I guess that's what, yeah, but if there is no other questions, then I'm going to stop here, and thank you all for joining me, and I guess have a good rest of the day. Okay.